Okay, guys, so another problem regarding heat exchangers. Again, another shell and tube heat exchanger. In this case, we're gonna have this. So there is this substance, which is H2O, going in the shell part, and it's going out again at the same temperature. Okay, so in this case, it means that this thing is not changing temperature, so it must be a phase change. Okay, this is actually H2O being condensed. So this one is a hot one. Okay, so let's just put something here. H2O, this is data, okay, and it's going in at 120 degrees Celsius, and it's going in at 120 degrees Celsius. It looks kind of weird, right? So this one is a hot one. I will let you know why. Because of what is the other substance? The other substance is the cold one, and it's going in at 30 degrees Celsius, and it's going out at what do I have here? 100 degrees Celsius. Okay, so this one is like a special case for heat exchangers. It's not very special, but it's something that we need to take into account, which is phase change. In this case, we have this. So I have this substance that it's going through a phase change. It's called condensation. How do you know it's condensation? Well, I'm sorry, this is so wrong. Okay, so I'm gonna think that, okay, let's just put the hot one, and it's going like this because it's not changing temperature. So everything here is 120 degrees Celsius, and it's 120 degrees Celsius, but it's losing heat. Okay, because this heat should be going to another substance. That other substance is something that is going in at 30 degrees Celsius, and it's going out at 100 degrees Celsius. Okay, so that's what's happening. I mean, I have made a mistake here. This mistake is to think or to put this graph as if it was a counterflow heat exchanger. This is not a counterflow heat exchanger. This is just for illustrative purposes, okay? Just to show you how this thing should be, illustrated. So in this case, you see a horizontal line, which means the temperature is not changing, which means that the phase change is happening inside of this box. And another fluid, it's gaining something out of that condensation, which is the heat that this one is releasing. Okay, so I'm gonna solve this problem in two ways. I'm gonna use two methods. This happened in another video, but I'm gonna do it again. So what they are asking us, still there's a lot of more data, but what they are asking us to get is to get the area. Okay, so we need to know the area of heat transfer for this shell and tube heat exchanger. So let me just clarify this. When you look at shell and tube heat exchanger, you need to, okay, so how many passes through the shell and how many passes through the tube? That's an important thing to understand. In this case, what I have here is one pass through the shell, okay, and 4 passes through tube. Okay, so this is what is going on. So I'm gonna mess this drawing, but then I'm gonna change it. So this thing is going 1 pass, 2 passes, 3 passes, and then the 4th and last pass. That's what's happening there. So I'm gonna erase this, but that's what happened there. This is 1 pass shell and 4 passes tube. Okay, so how can we solve this? We're gonna solve it with 2 different methods, which is the method of DTML, or in Spanish, diferencia de temperaturas media logarítmica, or in English, which is logarithmic mean difference temperature. I think this temperature, no, sorry, temperature difference. Okay, so instead of it's TD instead of DT. Okay, but you get the picture, right? It's one method, and the other method is Epsilon and NTU. Okay, that's the, so I'm gonna solve it with both of them. And you will see that there's a little bit of an uncertainty, which in one of them, and the other one help us to solve this story. Okay, so here I go, guys. For this cold water, I have that the C is 4.184 kilojoules kilogram Kelvin. For this one, this doesn't have one, so this doesn't have a heat capacity. I will explain you why, and this explanation will lead us to actually a simplification of how to solve this type of problem. But this doesn't have, why not? And you will say, well, it's H2O, right? It should have the same value. Okay, so yeah, but this thing is changing phase. So whenever you're changing phase, heat capacity becomes senseless. It doesn't have any meaning when you are changing phase, because I will let you know why. Or it makes sense if you think about this, that it has an infinity heat capacity. Oh, okay, so well, slow down. So we're gonna go later to that point. What else is mesh? It says here. So this mass flow of this cold water, it's 2.5 kilograms per second. Got it. There's also the U. Okay, so we're gonna put here that the U. I should put it here. So the U of this box of this is 2 kilowatt square meters degrees Celsius. Okay, so that's data. I'm gonna put it here, 2000 watts square meters degrees Celsius. I don't want to confuse you. This one is our watts and this one's are kilowatts, but the data is the same one. Okay, so what should we do? Let's just do the one that has more uncertainty, and this one is this one that I want to show you here. This one. Okay, so whenever you see like a correction factor, you know you are talking about DTML. Okay, how do you know that? Well, because this correction factor, it's used for the DTML. You are correcting something that is kind of wrong. This wrongness comes from here. So this is the Q, this is the UA, the DTML, and then the factor. Whenever you have a heat exchanger that is not counter flow, therefore you need to correct it. You correct it with this graph. You're actually correcting with this number. So you need to get a number in this y-axis in order to put it in this formula. Okay, this is our unknown. This guy is not known yet, but we need to get it. This one, yeah, I know it. DTML, I should get it, I think. And F, we should get it. So I'm sorry, we don't know a lot of things, but let's just try to have a hold on this one. Okay, let's start with DTML. So for DTML, we're gonna think that it's counterflow. This thing over here is delta TA, this thing over here is delta TB. Therefore, the TML, or for you English guys, LMTD, this one is going to be delta TA minus delta TB. And everything's going to be divided by the logarithm of delta TA divided by delta TB. Okay, so let's just go and put some little numbers there. So if I'm not mistaken, this one should be 20, which is 120 minus 100. Minus the other one, delta TB, which is a lot more, which is 90, I think. Yeah, it's 90. Logarithm of 20 divided by 90, which is 2 divided by 9. Therefore, my DTML in this case, it's around 46.54 degrees Celsius. Whoops. So no problem so far. I got this guy. Therefore, I can get it and put it here. What about you? You no problem. What about Q? Can I get Q? Oh, let's just see. So we're going to start Q. If you see here, I don't have a lot of data for the condensated of this steam, right? But I think I have everything that I need from the cold water. So let's just use for the cold water. This is going to be M of mass flow of the cold water, C of the cold water, and delta T of the cold water, which is 100 minus 30. Okay, so this one I don't know. Yep, and everything is yep on the right hand side of this equation. Therefore, this one is 2.5 times the 4.184 multiplied by 70. Therefore, my Q here, it's about, I already have it here. So you check this out. Please never trust what a guy in a blackboard is doing. You should always check it. Okay, so kilowatts. And therefore, whoop, you already have this amount of heat being transferred from the condensate to the cold water. Okay, good. We are approaching to the end of this because yeah, I already have this one. What about F? Yeah, the F is the only thing that is missing in order to get our A. Well, here starts the problem, guys. Hopefully you see it. Let's just start with the big problem, this R here. So this R means that this guy is 120 degrees Celsius and this guy is 120 degrees Celsius. So boom, right from the start, you have this guy that is 0. Therefore, R equals 0 right away because the numerator is 0. Okay, so I don't know you guys, but maybe you can see here is the 4, 3, 2, you know, but there is no this curve. I would like to see this curve that is R equals to 0, but there is nothing like that. So it starts to get a little bit off this problem for this method. Now for P, you can actually calculate P. I think you can calculate it. And this P would be around 100 minus 30 divided by 120 minus 30. Okay, so this guy will give me 0.7077. So yeah, I can locate myself kind of around here. Okay, so let's just see here. I can throw a vertical here. Well, I'm doing it just with hand. And then there's no way to know where the hell this r equals to 0 curve lies. Maybe it's closer, or maybe it's more here, or what the hell is going on. Okay, so you can do like an extrapolation, say, you know what, 0.4 and 0.2, they are divided this way. So maybe I can picture that my 0 curve will be, you know, maybe around it, but this thing doesn't look very linear, because I don't know if you see, guys, but 0.6 and 0.4 are closer together. 0.8 and 0.6 are closer together. 0.1 and 0.8 are closer together. So it seems that if I want to extrapolate from 0.2 to 0, I need to go farther away. Okay, so going farther away, I don't know if this thing is gonna be there or not. I mean, how much farther to my right should I go in order to put this curve? And I don't know if this curve is right or wrong. So you get the picture that this thing is kind of a little bit difficult to place it with a numerical value. I mean, you can put something there and still maybe get the picture that this thing is gonna be really up. So if you wanna get, you know, a value for this f, and if you're thinking that your curve is around here, therefore you can convince yourself that f should have a really high value. It should have like 0.95, but it actually depends on where you are imagining this r equals to 0 curve. Another thing that you can think is that, well, if they didn't put the r equals to 0 curve, maybe there's no r equals to 0 curve, and that could be a good assumption. So what I want to tell you here is that we don't know. Okay, so we are just elucubrating about if this thing is right or wrong. Okay, so what would you say? So if you want to have a value, so you need to make a lot of assumptions. So I'm going to do this assumption. So Q equals to U, A, DTML, and the F. I'm going to think that my F is 0.95, but remember, okay, so I'm just expecting that this thing could be a little bit like that, but actually we don't know. Okay, so if you want to end the problem with this, you can say, well, you know what, A equals to 7032.2 kilowatt divided by how much is this U? Okay, it was 2 kilowatts. Remember, 2 kilowatts times the DTML that I already know. This one is without uncertainty, and this one is with uncertainty. This 0.95, we don't know. We think it's like that. So this thing will give me 8.28 square meters. So this is when this way of solving heat exchangers is a little bit off, because we don't know too much. These graphs are kind of not unreliable, but we don't have all the information that we would expect, at least for condensation. For condensation, this guy got us to 0, therefore we cannot do much but imagining or assuming and like that. So I have a number there. We don't know for sure, but okay, so let's move on to the other method. The other method, I would say, is the best method, because it lets you to solve a lot of things without a lot of unknowns, by the way, and you don't use graphs. I mean, you use graphs, but you use it with high certainty, with a higher certainty, okay? Because you have more information there. This one is a good estimation, but just we are lacking, you know, this information, so we are just stuck there. Okay, so moving on, guys. Let's just start with effectiveness. Effectiveness is delta T of the one that is higher. So delta T, which C equals to C minimum. What I mean by this is delta T of the substance that has the C equals to C minimum. I have already explained that in another video, so you can think about what is going on with this. and this delta T is delta T maximum. Okay, so here it goes. Let's just go back to our box. Delta T maximum is easy to see, is the highest one. So this one is the highest one with the lowest one. So this is the lowest one. That's my high, this is my delta T maximum. This is the highest gap of temperature inside that box. So therefore I have my 120 minus the 30. Okay, so that is known. Now about this one, we need to figure out which one of these two, whether it's this water being condensated or this water being heated, which one of those has the minimum C. And it's pretty easy to see because this one is with the minimum C. Why? Because this has C that it's going to infinity. How do you know that? Well, okay, so quick thermodynamic review. C equals to Q divided by delta T. Broadly speaking, it's like that. So how much heat you can transfer to a substance and how much delta T that substance is suffering. So I don't know you guys, but if you see, I already know that I'm transferring 732 points. So I have a value for this one, and this value is 0 because I'm not changing anything, my temperature, right? That's what the condensated is saying. Therefore, this one tends to infinity. Every phase change has this value as infinity. Every substance that is changing phase doesn't have a numerical value of heat capacity, it tends to infinity. Therefore, this one, of course, is not the minimum, it's the freaking highest, okay? So this one is C max, this one is C max, I'm just gonna put it here. So this one is C max, and this one is C min, okay? So therefore, I know that this delta T is for the cold water being heated, okay? So I'm gonna put here that this guy goes from 100 minus 30. Okay, that's what's happening there. And if I do that, I will get that this indicator is actually 70 divided by 90, therefore 0.7077. Okay, that's what I have for this effectiveness. Now let's just go to the other guy, which is NTU. So NTU equals to U, A, and C minimum. I already have C minimum, good for me. I don't have this fella, but I have this fella, so I'm lacking this guy. I can use a graph in order to get it. So I think I have presented that in another video. I'm not going to do that on this one, but you have effectiveness here. You have NTU. It's in every textbook of heat transfer. You can find these graphs for this particular shell and tube heat exchanger. Okay. Remember that this one is 1 pass and 4 tube passes. Okay. I'm sorry. Oh, shell. I need to put that. This is important. Just don't. One pass doesn't mean anything until you say which pass you are talking about. So in this case, it's 1 shell, 4 tubes. Okay, that's the basic idea. And I'm sorry, I said that in the wrong way. There are no 4 tubes. I don't know how many tubes there are. I'm just saying that those tubes that there are passing 4 times inside the box. Oh my God, this is, yeah, you need to be careful with the language. Therefore, these types of graphs are used like this when these curves, what they mean is that you are using C min divided by C max, which in this case is pretty easy. If this fella is infinity, therefore, for this case, for the condensation or phase change, this number is always equals to 0. So you have a simplification. So you can use these graphs. I'm not going to do it, or you can use a formula. So there is a very simple formula to calculate this unit number of transfer units when you have condensation. So when you have condensation, congratulate yourself because the problem, mathematically speaking, is easier. Therefore, I'm gonna put the formula here. If I can locate it here in my notes, yeah, I already located it, minus logarithm of 1 minus the effectiveness. Okay, so it's a very simple short formula for these NTUs in terms of the effectiveness that I already have. So no problem, and I just need to calculate this one, and this one will give me 1.504. Therefore, I already have this fella, and I can calculate the area right from the algebra. So I don't know you guys, but I can do this, the minimum divided by the U. Therefore, area for this method is 7.866 square meters. I don't know you guys, we didn't were really happy we weren't really happy about this method because it was really uncertain, but it doesn't seem very far away from that. So this value of f seems kind of reasonable. We don't know if that's the true value, but at least we can feel that, okay, so these two methods gave us a little bit of the kind of the same area. I mean, it's not the same area, but it's kind of the same area. Okay, guys, so that's it with this example. See you later in another video. Okay.